Hello everybody and welcome back. In this video we're going to be looking at C3 on our Canadian Open paper. What have we got? Alphonse and Beryl play the following game. Two positive integers m and n are written on the board. On each turn, a player selects one of the numbers on the board, erases it, and writes in its place any positive divisor of this number as long as it is different from any of the numbers previously written on the board. For example, if 10 and 17 are written on the board, a player can erase 10 and write 2 in its place. The player who cannot make a move loses. Alphonse goes first. Okay, so a player who cannot make a move loses. What would that look like? Well, suppose if you had a prime number and 1 left on the board, you'd be stuck, because you couldn't erase P and write P. And you couldn't erase P and write 1. And of course you can't erase 1 and write 1 either. But if you had a game maybe that started like 10-2, you couldn't take the 10 away and turn it into a 2. Actually, if you started with, say, something like 10-10, that would be interesting as well. Because you could get rid of this 10, write a 5, and then get rid of this 5 and write a 1. And then I suppose you could get rid of this 10 and write a 2. But yeah, it looks like it might just come down to prime 1. Something like that. That might be what all the loses or lost positions look like. Anyway, A part. Suppose that m is 2 to the 40. So all the factors of m are going to be powers of 2. And n is 3 to the 51. So these are different primes. So any number found by erasing something in the n position is going to be different than something found by erasing the 240 or anything over there, with the exception of 1. I guess you can always... The greatest common divisor is always sort of going to cause a little bit of a problem, but we don't have much of a greatest common divisor here. I'm interested as to why it's 40 and 51. That's what I'm more concerned about. Anyway, suppose we got these numbers. Determine which player will be able to win the game and explain the winning strategy. Okay, well, it is a Part C question. We should be explaining things. Now, with a question like this, the 40 and the 51, these are really big numbers. I think it might even just be easier to try a simpler game. You know, try something like 2 to the 2 and 3 to the 3. That way, the power of 3 is still using a higher exponent. Okay, and who? Alphonse goes first? I assume, because he's A. Yeah, Alphonse goes first. Okay. So, suppose Alphonse just took this 4 here, which is technically what it is, and turned it into a 1. Then, is the other person Beryl? Yeah, Beryl. Okay. Then Beryl could write a 3 here, and Alphonse would lose. So he doesn't want to do that. But if he drops the 4 down to a 2, Alphonse could just write, or Beryl could turn the 27 into a 1, and then he'd lose. So definitely doesn't want to focus on that. So I guess maybe he would put a 9 here. And then what's Beryl going to do? Because then Beryl's looking at sort of 2 to the 2 and 3 to the 2. And if Beryl drops either one of these down to 1, then the other person can drop it down to the other prime. And if Beryl drops, say, that down to a 2, then Alphonse can drop this down to a 1. So he can definitely win in this sort of scenario by bringing it down to sort of 2 to the 2 and 3 to the 2. But what if instead we started with 2 to the 2 and 3 to the 4? Well, no, the same reasoning should work. So how about we start with 2 to the 3 and 3 to the 4? So what could we have? Well, if it's Alphonse's turn, I guess if he drops this down to the 3 to the 2, then we get the same play out as last time. Nothing particular. So what if it was 3 to the 3 and 2 to the 3? And what I'm doing here is I'm just experimenting with a small simple case to try and understand how the game works. and to maybe understand and develop a strategy and or just an intuition as to who I think might win. So if Alphonse did that, then what's Beryl going to do? Well, she could do 2 to the 2, and then Alphonse would be looking at 2 to the 2 and 3 to the 3, but we know he wins that. Or 2 to the 1. Oh, you know what might be an interesting strategy here is dropping down so that the degrees are equal. Because if Alphonse on his turn makes the degrees equal, Beryl on her turn will have to make the degree something less. And so Alphonse just drops it down again. And then... Well, hold on. So, but if... Yeah, if we reach all the way down to 2 to the 1 and 3 to the 1, then Beryl could do 2 to the 0, which is 1, and Alphonse can't follow, so then he would lose. So he might... So that might be a losing strategy, almost. But I like the simplicity of that. So, what this really looks like is prime to the A, prime to the B. That's really what we're looking at for this game. 2 to the something, 3 to the something. So, and we'll say that B is greater than A. If you drop it down like this, as long as A is greater than 1, you can keep doing this quite comfortably. I think maybe we should work backwards. So, let's get rid of all of this, and we'll make an observation. So, really simple observation that might be worth a mark or two. Let's say the only time we'll get a number that being written down that is repeated. Well, no, that's not the right way to say it. So the only factor of 2 to the 40 and 3 to the 51 in common is 1. So once a 1 is written down, then a 1 cannot be written down again. Okay. Now, I'm going to start by saying, notice that anyone who starts their turn, which I spelled like a bird for some reason, I'm kind of spacing out here, starts their turn with P1 as a with P as a prime, will lose. I don't think this needs to be justified, but if you wanted to, you could say, well, what possible options do they have? They could erase the P and write a 1. Oops, they can't do that. They could erase the P and write a P. Oops, can't do that. Erase the 1 and write a 1. Oops, can't do that. If you want to write that out, that's fine. I don't think it's necessary. So the question is, all right, so we know how to lose. And this is sort of almost the only simple losing position. Right? So I wonder if a strategy for barrel to win would be... Just thinking. If we're looking at P to the... Now I'm just sort of musing about the whole thing. A strategy... might be keep A minus B equal to 1. That might be a good idea. Something to think about. Yeah, Alright, so the P1... So, what could lead to P1? So we're sort of using the game theory strategy of working backwards from losing position. And anything that can give you, can leave your opponent with a losing position is therefore a winning position for you. So you could have P to the anything and 1. So that's a winning position. Or if you're looking at P and Q to the anything, then that's a winning position. For B greater than or equal to 1, and for A greater than 1. Okay. Now, what can we do from there? So any position that is... So the next you got to sort of force the person into a losing... So what if I start my turn looking at this, I know I'm going to win. If I start my turn looking at this, I know I'm going to win. So the question is, what can I give? What's sort of the turn preceding that? So if you had something like P squared Q to the B, you would know you were going to lose, right? So to go backwards from this winning position, you can't have reduced to this, so you have to reduce to this. So you could also have P to the A Q is a losing position, except we already know that that's a winning position if the exponent here is greater than or equal to A, the exponent here is greater than or equal to 1, so we need A to be equal to 1, I guess. So I want them to hand me something with 1 and a power of a prime and a non-zero power of a prime. Well, actually, it's got to strictly be a power of a prime, not just a prime itself. Actually, wait a minute. No, B greater than or equal to 1. No, this is automatically a winning position. So we don't want them to have that. So there's no way to go backwards from our first winning position to give them a losing position. So the idea behind a losing position is they are, so whatever losing position they have, let's say, let's use a C and a D so we don't get confused with our indices. A losing position would then be forced to go to one of these two positions here. So you're either looking at Q to the D being just Q, because then when you choose that side it has to be 1, or you're looking at P to the, but if you gave them that, why couldn't they choose PC? Well, I suppose if it was just PQ. So PQ is a losing position. Wait, no it's not. It's a winning position. Again. This is pesky. What would P squared Q to the B be? And we'll say make it just Q. Right? You could either go to P squared 1, but then they'll give you P1. Or you could go to PQ, and they'll again give you P1. So P squared Q is a losing position. Except, couldn't you just go to 1Q? And then they would lose. So P squared Q is a winning position as well. So I had a flash of insight for a moment. What if we were looking at, by the way, I'm using P and Q, just the 2 and the 3 don't matter, it's just they're primes. I'm trying to be general, because I haven't read B part of the question, which might have other primes or something like that. So what if we tried to keep A minus B equal to 1? And we were looking at, say, 3, 4. Okay, it's Alphonse's turn, so he's going to give P cubed Q2. And so now it's Beryl's turn. What could Beryl do? Well, we could get a Q and a P3, but then Alphonse will win on the next turn. We could have a 1 and a P3, but then Alphonse will win on the next turn. We could have P squared Q squared, I guess. And then Alphonse on his next turn would probably do P squared Q. But then Beryl will do 1Q, and Alphonse will lose. So Alphonse wouldn't want that. So basically, you can't be the first person to drop to a single prime. If you're the first person to write a prime or 1, you've lost. That's it. So, other than that, what can we conclude? Again, I'm spelling turn wrong for some reason. I don't know what's up with me today. So the first person to write a prime or 1 on their turn loses. Okay, now how do I force someone to write a prime? So P squared Q squared is a losing position. But PQ was a winning position. So, what about PQ? So maybe it does come down to equal powers. So P cubed, Q cubed. You could, so if I saw that, if maybe it alternates, maybe if it's P odd, Q odd, you win, P even, Q even, you lose. That might be something. So maybe Alphonse's strategy is, I don't know yet. So if I had P cubed, Q cubed, and I gave them P squared, Q cubed, because I definitely don't want to give them P Q cubed or 1 Q cubed. So if I gave them that, they don't want to give me... No, they would want to give me P squared, Q squared, which is a losing position. And so P cubed, Q cubed is a losing position. Okay, so I think I have an idea. We claim P to the A, Q to the A is a losing position for A greater than or equal to 2. And of course, P and Q primes. So you have to explain that. If you wanted to, you could just write 2 and 3 here. But I'm trying to be more general, because I think it's an interesting game that they've got. So we claim this is a losing position for A greater than or equal to 2. And if that's the case, then what's our strategy? Well, then Alphonse should win, because on his first turn, he'll turn this into 3 to the 40. Okay. So indeed, P squared, Q squared is a losing position, as one who receives this must write P Q squared, P squared Q, 1 Q squared, or P squared 1, and then lose. Okay. Now, suppose P to the A, Q to the A is a losing position. We'll prove P to the A plus 1, Q to the A plus 1 is also a losing position. Okay. So, if given P to the A plus 1, Q to the A plus 1, our options, I'm going to say without loss of generality, just so I don't have to keep writing all the P cases and Q cases separately, are to give P to the... So we could give them 1 Q to the A plus 1, or P Q to the A plus 1, or P to the B Q to the A plus 1. I'm saying A is greater than or equal to 2, with B greater than or equal to 2. And we might label these cases 1, 2, or 3. So in 1, we'd lose as the other player would give 1 Q back. For 2, we'd lose to the next move, which would be P1. They'd eliminate everything on this side. And then finally, so that was case 2, case 3. We'd get back P to the B, Q to the B, a losing position, as B is said to be greater than or equal to 2. These are the only things that could happen. Of course, there's symmetry. They could instead remove things off of the Q pile, but it's all symmetric. Okay, so since we know we start with 2, both exponents being 2 being a losing position, and we've just shown that if P to the A, Q to the A is a losing position, then P to the A plus 1, Q to the A plus 1 is a losing position. By induction, I think specifically strong induction, you can just say by induction, P to the A plus 1, Q to the A plus 1 is a losing position. Or, well, let's just say P to the A, Q to the A is a losing position for A greater than or equal to 2. So Alphonse can win by making his first move. We start with 2 to the 40, 3 to the 51. He will leave barrel with 2 to the 40, 3 to the 40. Okay, so even exponents did work out, or not even, equal exponents did work out, but I was sort of flustered by the PQ case, which really sort of tripped me up. I thought it was a nice pattern there, but no, it's all fine. Okay, so that's A. Now let's get to B part. Suppose that M equals 2 to the 40 and N equals 2 to the 51. Determine which player is always able to win the game and explain the winning strategy. So same thing, except now we've got powers of 2 can appear for both numbers. And so, for example, on our first move now, Alphonse can't write 2 to the 40, 2 to the 40, because 2 to the 40 was already written. So, what can we do? What can we do? Well, as always, I would look at a small, simple version of the game. Okay? This version of the game is P to the A, P to the B. And you can assume A is less than B. What could Alphonse do? Well, he could drop down to a 1 here, and Barrel could give a 2 here. And so then Alphonse would lose. He could drop down to a 2 here, and then what could Barrel do? A 1. So, would lose. And you can't do 2 to the 2 and 2 to the 2. So I think 2 to the 2, 2 to the 3 is a losing position for Alphonse. But if it was 2 to the 2, 2 to the 4, 2 to the 2 and 2 to the 3 would make a losing position for Barrel. So, what can we say? Well, once again, 1P is a losing position. But we get some other issues. 1P squared is not a losing position, but 1P squared is a losing position only if P squared was the previous position. Interesting. And there the exponents differ by 1. So I wonder if maybe Alphonse's... I don't know. I'm not married to that strategy of exponents have to differ by 1, but I feel like it's a nice general rule of thumb, just like the keep exponents equal rule from part A. And it sort of keeps everything together. But of course, if I were presented p squared, I could just go down to 1p, and so p squared always leaves a losing position. So what could we say? So you can't even say that. Tricky. So pp squared is a winning position. Just give them p1. There's no way 1 has already been written. How about p squared p cubed? Well, didn't we just talk about that? Is a losing position. So, because what could happen? Well, p squared p cubed, what could I do? I could turn this into 1p cubed, and then they'd go with 1p, because there's no way p has already been played. I could do p cubed, and then they'd give me p1, because there's no way 1's already been played. They give me p squared p, and then I'll give them 1p, because there's no way 1 has already been played. I think that's about it. I guess you do p squared 1, but then p1, because p was never played. And you can't give p squared, because p squared has already been played. So either the p squared turns into a 1 or a p, or the p cubed turns into a 1 or a p. So now my suspicion might be p 2k plus 1 p2k is a losing position, and p 2k plus 1 p2k plus 2 is a winning position? That's my current hypothesis, just based on this work here. So if that's the case, can we prove this true? Well, clearly true for k equal to 0, because that's the 1p case. Suppose true for all k, and check p to the 2k plus 1, p to the 2k plus 2. Alright, so I claim that this is a winning position because I can force them to get a losing position. Just give p to the... Too many 2's. Just give p to the 2k plus 1, p to the 2k, as p to the 2k has not been played yet. Since both m and n were greater than p to the 2k. And so if I'm correct and this is a losing position, then of course this is a winning position. Alright, so then what do? Well, we also have to prove that this really is a losing position. So Suppose I'm given p to the 2k plus 1 p to the 2k. No matter what I do, I should then be able to be given a loss. So we either go p to the 2k plus 1 p to the a, and a is less than 2k, or we get p to the a, p to the 2k, and again a is less than 2k. So they should be able to get me back to a scenario like this where it's an even and then an odd, and the odd is bigger. Well, what if a were 2k minus 1? So I'm actually not as confident now. I'm going to call this 1 and this 2. And so now 1. If a is odd, a is less than or equal to 2k minus 1, and then I will give them p to the 2k minus 2, p to the 2k minus 1. Yeah. Well, no, p to the a minus 1. A is odd, therefore a is greater than or equal to 1, so a minus 1 is greater than or equal to 0. So that would work. What if a was even? If a is even, I want the even number to be the lower one. Then give p to the a plus 1 p to the a back. Okay. A is less than 2k. That's what we said. Therefore, a plus 1 is odd, and therefore less than 2k. So p to the a plus 1 hasn't been written yet. That's a concern we have to make this time. So this is okay. All right, case 2. Suppose I'm given b and a 2k. If b is odd, well, once again, b is less than 2k. Give back p b minus 1. Same reasoning, it should still work. If b is even, give back p to the b plus 1. Again, same reasoning, it should still work. B plus 1 is odd. It's less than 2k, so it hasn't been written yet. So now, I think Alphonse has the winning strategy. Oh, and since this is a winning position, if a smaller version of this is a losing position, if every smaller version of that is a losing position, and this is a losing position if every smaller version of this is a winning position, by induction we understand a sort of a win-loss strategy situation. So Alphonse has a winning strategy. If his first move, it was still 40 and 51, right? Yeah, 40 and 51. First move is to give Beryl 2 to the 40. Now, does he want 2 to the 39 or 2 to the 41? So if you're presented with a higher odd than your even, you will lose. Here, the odd is higher than the even. This is a loss. When the even is higher than the odd, it's a win. So odd higher than even, 241. And since p to the 2k, p to the 2k plus 1 is a losing position, by induction, Alphonse will win. Okay. So that took a little while. I liked the question. I also liked the sort of coincidence that my thought on how to do A, which is keep the powers close together, actually turned out to be a good strategy for B, and that my initial strategy of keep things equal actually turned out to be the right answer for A, even though I got a little confused. I like that. It was good. It was still a heck of a thing to write up, but usually for questions this late and when they're game theory ones, try and look at very simple strategies, you know, keep everything equal, look at parity, you know, so here oddness and evenness played a role. Oh, we have to describe the winning strategy, don't we? I don't think I've described the winning strategy for either one. So for A, well, I mean, technically I have because I've described the win-loss states, but for A, what was it? Alphonse keeps exponents equal until he's given 2 squared, 3 squared, no, 2 cubed, 3 cubed. Wait, hold on. What was the winning strategy in part A? So keeps the exponents equal until given one of p to the a1, p to the aq, with a greater than 1, we'll say b actually here, with b greater than or equal to 1. Actually, you could never be given that. Yeah. Well, I suppose this should be 2 to the a and 2 to the b. And gives 2, 1, or 1, 3. This should be a 3 back. Alright, so there I've properly described the winning strategy. What was the winning strategy for B? Alphonse will always give Beryl back a pair of the form, or not give, I say leave on the board maybe. Give a pair back of the form 2 to the 2k, 2 to the 2k plus 1 until 1, 2 is written. And the game ends. Alright, so I actually have described the winning strategy, although I would argue describing the win-loss states that we're going to use counts just as much, but I don't want to lose marks, so there we go. So as I was saying, game theory questions, always try and keep it simple. I mean, look at little things like mod 3 or mod 2, or keeping things equal. There are other more advanced game theory questions, but usually it's about investigating and finding the strategy, and that's what you saw me do there. I investigated, I played around with small, simple scenarios. Okay, so one question left to go, and then we've got the paper all finished off. I will see you for C4 in the next video.